first session is by Dr. Vishal Sahni. It's a great pleasure for me to introduce Dr. Vishal Sahni. Dr. Vishal Sahni is a lecturer in Faculty of Engineering at the Dirac Educational Institute. He obtained bachelor's degree in electrical engineering in 1999, MTech in engineering systems in 2001, and PhD in evolvable hardware systems in 2004, all from the Dirac Educational Institute. He has been recipient of President's Gold Medal of the Dirac Educational Institute twice, in 1999 and 2001. His research interests are quantum and nanocomputing. He has authored a book entitled Quantum Computing, published by McGraw-Hill, and co-authored another book on nanocomputing. He is on the review board of several journals, including IEEE Transactions on Instrumentation and Measurement, among others. Dr. Sahni is also the secretary of the DI Dayalbagh chapter and vice president of the Systems Society of India. And he is also the principal investigator of this event, CONSAS 2008. I welcome Dr. Vishal Sahni.
Good morning, everybody, and welcome to CONSAS. Thank you, Dr. Kalra, for such a nice introduction. And I'll start with this tutorial on quantum information systems. In fact, all of this is very elementary stuff, but I think it will help in building up momentum for the advanced school. I'll start with a quotation by Niels Bohr. Niels Bohr said that if anybody says he can think about quantum physics without getting giddy, that only shows he has not understood the first thing about them. His original quote was in German, and the word he used for dizzy is schwindelig, which is dizzy or giddy in English. The outline of the talk, we start with an introduction to quantum information systems, then some brief history, then qubits and quantum gates, Shor's and Grover's algorithms, physical realization and simulators, then some future applications of quantum information systems like 3D unicast and multicast scenarios. Gordon Moore gave a law that, in fact, it's a rule of thumb that every 18 months, the number of transistors doubles on an IC. We are coming towards higher and higher miniaturization. So the number of transistors on an IC has been increasing more or less according to that. Another way of looking at that plot is that the number of electrons required in the base of a silicon transistor has been decreasing rapidly. So what happens when we hit the unity mark? Do we compute with half an electron? You can't go beyond that. So very soon, maybe another decade, we will hit that. So what do we do? This is the Shockley won the Nobel Prize for the first transistor that is shown here. This is the relationship between quantum mechanics and information theory. Quantum computing or quantum information systems try to synthesize the two giants of the 20th century, quantum mechanics and information theory. Quantum mechanics is here with its allied fields like Hilbert space, entanglement, measurement, and so on. Information theory has its own fields like ideas like Shannon's theorem, compute Turing machines, cryptography, and so on. So quantum computing has a prime position, and it takes ideas from both these fields. This is the relationship between classical information and quantum information. At present, what we are working on is a subset of quantum information, and we are trying to develop information technology systems which can work on both. Some bit of history of quantum mechanics. Isaac Newton thought that light was made up of particles, though he was aware of the diffraction and interference phenomena, which were indications that it behaved like waves. At the beginning of the 19th century, Thomas Young, a British physician and physicist, conducted the famous double slit experiment on light, demonstrating the wave theory effect of interference. This is Young's double slit experiment. He shone sunlight here on a slit, and then there were two slits. Now, if you open just one slit, this is what you get. If you open both the slits, this is what you get. If you assume that light is a wave, what you get should be this. If you assume light is a particle, what you get is this. But what is observed is in fact this. Some effects of light can be explained by assuming it as a wave. Some can be explained by assuming it as a particle. So in fact, it is both. That is the wave-particle duality of light. Then Max Planck classical thermodynamic predictions were in contradiction with the experimental results at higher frequencies, where the measured intensity, rather than increasing like mu square, was increasing exponentially. He proposed the theory of black body radiation, that energy is released in packets or quanta or bundles, 0, h mu, 2 h mu, or multiples of that n h mu, where h is the Planck's constant. In 1905, Albert Einstein showed that the empirical properties of the photoelectric effect could be explained by assuming that light consists of particles, each one of them having an energy h mu and moving at the speed of light. Einstein's light particle later on became known as a photon. Bohr postulated that the angular momentum of the orbiting electron must be a multiple of the Planck's constant divided by 2 pi. So mvr is the angular momentum, that is a multiple of h upon 2 pi. Where mvr is the classical definition of the angular momentum, m is the mass, v is the electron velocity, and r is the radius of the electron orbit. The next significant step was made by the French physicist Louis de Broglie in 1923. Drawing an analogy with light and its dual character as both a wave and a particle, de Broglie proposed that a wave should be associated with every kind of particle, in particular with the electron. De Broglie also proposed an equation that linked the momentum p of a particle to the wavelength lambda of the wave associated with it and Planck's constant. So p is h upon lambda. Then we come to Erwin Schrödinger and Paul Dirac. In 1926, Schrödinger and Dirac showed the equivalence of Heisenberg's matrix formulation with Dirac's algebraic one using Schrödinger's wave equation. Then in 1926, Dirac and independently Born, Heisenberg and Jordan obtained a complete formulation of quantum dynamics that could be applied to any physical system. The first calculations were done for the hydrogen atom. Then we come to John von Neumann. He was a great mathematician. In 1926, John von Neumann introduced the concept of Hilbert space to quantum mechanics. The idea came to him while attending a lecture of Heisenberg, who was presenting his matrix mechanics and the difference between his model and the one based upon Schrödinger's wave equation. During the presentation, David Hilbert, considered one of the greatest mathematicians of the time, asked for some clarifications. So from that he got the idea. Then John von Neumann decided to formulate the quantum theory in terms familiar to the great mathematician. I jump maybe 50 years and come to more recent ideas and quantum algorithms. So we come to 1985 when Deutsch's algorithm came. People were trying to put together quantum mechanics and information theory. So Deutsch's algorithm demonstrates tasks quantum computers can perform in one shot that classical takes 2 shots. Then further improvement, 1982, Deutsch-Jozsa, exponential separation, Bernstein-Vazirani, 93, super polynomial summation, Simon's algorithm, 94, exponential separation. 94 came Shor's algorithm, which we'll see later. It demonstrates that quantum computers can efficiently factor numbers. Factoring is such a great problem because all our cyber security is based on factorizing large numbers. Then 1996, Grover's algorithm, which demonstrates quantum search as polynomial speedup over classical search. We come to quantum bits. A qubit, as distinct from a classical bit can be either 0 or 1. A qubit can be in a state other than ket 0 and ket 1. It can be in a superposition of both. So ket psi is alpha ket 0 plus beta ket 1. This is the matrix representation of this qubit. Now what is so surprising about qubit is that suppose we have got 2 4-qubit quantum registers. 2 to the power 4 is 16. So the first register can hold 16 values together. The second register can also hold 16 values together. So if we add 2 quantum registers, A plus B gives us all the 256 answers simultaneously. If you do that using a classical computer, you will have to add, you will need 256 steps. Of course, several answers will be common, but you need to go through all of them. Then we have a quantum NOT gate. A classical NOT gate just flips it, 0 to a 1, 1 to a 0. A quantum NOT gate converts alpha ket 0 plus beta ket 1 to alpha ket 1 plus beta ket 0. This is the matrix representation of the quantum NOT gate. If you multiply the input with the matrix representation, it works. Then quantum Z gate, it leaves ket 0 unchanged and changes sign of ket 1 to -1. Again, the matrix representation. Hadamard gate is another interesting gate. It converts a 0 to 0 plus 1 by root 2 and 1 to 0 minus 1 upon root 2. This is the matrix representation. So you can see if you give the input as alpha 0 plus beta 1, what you get is this. Then this is some summary of action of Hadamard gate. If this is the input, this is the output. 1 gives 0 minus 1 by root 2. Superposition of both alpha 0 plus beta 1 gives this. You can rearrange the terms. 0 plus 1 by root 2 gives us back 0. 0 minus 1 by root 2 gives us back 1 again. Then we have got the Pauli matrices, sigma 0, sigma x, sigma y, and z. Then control NOT gate. In a control NOT gate, we have got, it's a 2-qubit gate. The top line is the control qubit, the bottom line is the target qubit. If the control qubit is 0, nothing happens to the target qubit, it goes as it is. If the control qubit is 1, the target qubit is flipped. So you get all these 4 combinations. If control qubit is 0, target qubit is flipped. If is not flipped, if it is 1, it is flipped. Then this is the matrix for the CNOT gate. It's a 4 by 4 matrix. This is the swap gate. A swap gate interchanges 2 qubits. Basically, you have got 3 CNOT gates arranged like this, or it is also represented like this. At the end, you get BA instead of AB. So this is the swap gate. Matrix representations of quantum gates and circuits. It's the outer product of sigma in ket input with the Bray output. Example of the NOT gate is shown. This is how you get matrix representation of gates. You can develop the matrix representation for swap gate, sum it over all the 4 possible combinations. This is the final matrix. This is the Pauli gate. This is a 3 qubit gate, control, control not. The first 2 bits are control qubits, which remain, and the last one is the target qubit. The first 2 remain unaffected. You get them as such. The last one is flipped if both A and B are 1. Else it is left unchanged. Then we have got Bell states or EPR states. EPR stands for the name of 3 great scientists, Einstein, Podolsky, and Rosen. They gave the famous Bell states or entangled states. What is so interesting about them is that this is the circuit for realizing Bell states. If you give this the input, the output of the Hadamard gives 0 plus 1 by root 2, and then we've got a control NOT gate. So we end up with 0, 0 plus 1, 1 by root 2. What is so interesting about this is you can't break it up into 2. No single qubit gates, ket A and ket B, such that you can split it up into 2. So these zeros are together, this 1 is together. Now suppose I measure the first qubit and I get a 0. I am certain to get a 0 in the second qubit as the measurement. This is very surprising because suppose I have got 2 qubits entangled here. One is here, I take one to maybe the United States, and I get the measurement here as 0. It is certain that that qubit will also give 0 upon measurement because of, even though they are separated far, there is no communication between them. Einstein called it spooky action at a distance. So similarly for all the other states. Then of course, Dr. Bennett is here. He discovered quantum teleportation with his colleagues. Suppose Alice and Bob are 2 friends. We have seen human teleportation in science fiction movies. You get into a machine, press a button, you come out somewhere. In quantum teleportation, you are transferring quantum information. Suppose Alice and Bob are 2 friends who met a long time ago. Before they separated, they generated a Bell state, and each one of them took 1 qubit. After several years, Alice wants to send a qubit ket chi to Bob. However, she can send only classical information. The problems are, number 1, Alice doesn't know what she has to send. The surprising thing is Alice can't measure what she has to send, but she can send that. And second thing is she can communicate only over a classical communication channel with Bob. This is the circuit for quantum teleportation. The top 2 lines are Alice's qubits, the bottom line is Bob's qubit, and this is the entangled state shared between them earlier. Now what happens after the CNOT gate? This is ket chi 0 is the initial state. It is ket chi beta 0, 0. After the CNOT gate, you end up with ket chi 1. After the Hadamard gate, you end with ket chi 2. Now, if you look closely at the last expression, you can see 4 distinct parts. 0, 0, alpha 0 plus beta 1, 0, 1, this, 1, 0, alpha 0 minus beta 1, 1, 1, alpha 1 minus beta 0. Now, there is a measurement performed by Alice. There are 4 possibilities. Alice measures a 0, 0, 1, 1, 0, or 1, 1. In either case, the corresponding term is now teleported to Bob. So, if Alice measures 0, 0, Bob ends up with ket chi. If Alice measures 0, 1, then Bob ends up with alpha 1 plus beta 0. He can always get back the original state by multiplication with an X gate or Z gate and so on. This is just a photo of a quantum entanglement setup. Then quantum communication channels are also very interesting because any eavesdropping is detected by error in the check bits. You will hear more of this in the talks. I have just tried to give a brief idea of quantum ideas. Alice and Bob will always be able to discover that Eve has been listening to the line. Some communication setup used to verify. This is in fact commercially available. A company in Geneva is making it quantique. Then we come to Shor's factoring algorithm. Factoring is at the heart of cyber security. RSA crypto system stands for Reverse Shamir and Edelman. They gave this crypto system. Basically, you have to factorize a very big number. Multiplication is easy one way, but if I ask you 29083 x into y, you can't break it up into 2 so easily. So Shor's algorithm reduces factoring problem to order finding. Factoring is important because all your cyber security, bank transactions, credit cards, they are based on factorizing a very large number. You have one part of the factor, the other side has the other part. So when both you send your part over there, they multiply it and check whether you have that. So if somebody is able to develop a quantum computer which runs Shor's algorithm, then all the cyber security which is currently there will break in a matter of seconds. So just an example, suppose we have to factorize 21. It's a toy problem. You choose n is 21 and any number x between 1 and n minus 1. And then compute XR mod n. What is interesting about this is the terms repeat 1, 2, 4, 8, 16, 11. So the order is easily seen to be 6. So you can always compute the other factor. Then the use of quantum computers for order finding is that using quantum Fourier transform circuits, this operation XR mod, and you need not do it for every step. You can do it together for all the states using a quantum computer. So the factoring problem is equivalent to the order finding problem, that is Shor's result. All the steps in the algorithm can be performed efficiently on a classical computer except the order finding part. Grover's algorithm is used to search an unstructured database of size n in order root n. Suppose you have an unsorted database of maybe 10,000 names and you want to look up a particular name. If you are lucky, it might be the first name. If you are unlucky, it might be the last name. You might have to go through all the 10,000 entries. On an average, you'll need at least n by 2 lookups. So, but Grover has come up with an algorithm in which you can search it in order root n. Only 100 lookups will give you the answer. So he has used an oracle. Oracle is a black box which does not know the solution to a problem, but can recognize it when it comes. This is the schematics circuit for Grover's algorithm. This is the oracle workspace. These are the Grover's iterations which are performed. I prefer to explain it graphically. Suppose you have got total n states, and out of those n states, m are what you are searching for. So the n minus m are the unfavorable states. So alpha is the set of all the unfavorable states, beta is the state of all the favorable states. So this is the initial state. What happens is first the Grover's oracle is applied. That is like a reflection about this alpha. So you come here after the oracle, and then when you multiply it by 2 ket psi, bre psi minus I, you come back to the third final state. And 2 reflections is like a rotation. So slowly and slowly what we are doing is we are rotating the initial state from 1 towards beta. So each Grover iteration is a rotation by an angle theta, where cos theta by 2 is this. So slowly and slowly we are trying to come to the final state. Physical realization of quantum computers, the basic requirements for quantum computation, robust representation of quantum information, performing universal family of unitary transformations, then initial states. You should be able to measure the output result. Several techniques have been tried. Optical photon, in fact, several of them have been successful. Optical photon quantum computers. It is work in progress. It is quite possible that optical qubits will find a natural use in the communication of quantum information, such as quantum cryptography, rather than in communication. Then optical cavity quantum electrodynamics. Ferro cavities have been used with 2 plane mirrors. Then ion traps. Electron and nuclear spins provide potentially good representation for qubits. The drawback is the experiment performed have used only a single spin and only 2 qubits, which is not useful for computation. However, these technical limitations may someday be overcome and lifetimes can be extended by technological surprise. Maybe these trapped ions could be register of qubits in a quantum computer someday. NMR quantum computing, of course, has been successful. Direct manipulation and detection of nuclear spin states using radio frequency electromagnetic waves. And people have created 7-qubit quantum computers. Latest advances could lead to computers that use qubits for information processing. Silicon quantum computers. The advantage of silicon is all our existing infrastructure is built using silicon. All our facilities are working on silicon. So if somehow we are able to make silicon quantum computers, our existing investment is not going to waste. We can still use it. The advantage of using silicon is that we are familiar with it from years of building classical computers. Donor nuclear spins are well isolated from environment. It has low error rates and long decoherence time. Of course, presently, if you are in a lab and you don't have access to these physical facilities, it doesn't mean you can't start working on a quantum computer. So you are coming from all over. You might not have an NMR machine in your lab or something, but you have got software simulators like Qubit simulator, and you can start playing around with quantum gates and see their effect and circuits on a desktop PC. You can they have quite good support, Hadamard gates and CNOT gates, several other things. Then CAD for quantum computer simulator, QCAD. It is a graphical designing environment for quantum circuits, quantum simulator for several gates. This is some QCAD examples. Then QUACK, there's a quantum computer simulator for MATLAB also. Computer science people like to use MATLAB. All the commands operate from within the MATLAB environment. You've got single qubit and Bell state preparation, single qubit unitary gates, control knot, quantum Fourier transforms, Bell measurements, classically controlled operations, density matrices, and so on. Teleportation, we just saw. In fact, we've developed a quantum QUACK code for teleportation. You can verify that it works. This is the MATLAB output. So even in MATLAB, you can verify that, start playing around with quantum gates. Now we come to some new ideas. we have got 3D video conferencing right now, but later on in the maybe another 50 years, we can have perhaps 3D video conferencing using teleportation, so that we are safely ensconced here in this room and we are transmitting this to maybe 200 other places. And what is transmitted is not physically the particles are transmitted, but every information about every particle is transmitted there. So you can have something like this, that maybe suppose we are here, you have got 2 cameras. This is a very rudimentary idea. Then you have a quantum encoder which converts this audio and video and 3-dimensional information, and that is sent in the form of a qubit. At the other end, you might have a quantum decoder and a 3D projection system, something like that. But one thing is that entangled states have to be created beforehand. The transmitter and receiver have to have entangled states beforehand. They could be carried around on a pen drive or USB token someday. Right now you have optically photons which are entangled and things like that. But if this has to work commercially, you need something better. This is maybe, then what do you do for a multicast? You can't copy, you have the no copying you can't clone a quantum state. So you have the no cloning theorem. What do you do if you have to do a multicast? Then maybe you will need several entangled states like this. You have got a single location which is transmitted. And several entangled states. The first qubit is entangled with the first receiver, second with the second one, third with third one, and something like that. And at every end you have got 3D images at the receiver ends. But now each receiver has to have its own bank of entangled states shared with the transmitter. It might become as simple as a SIM card someday. This is just my book on quantum computing. We have got collaborations with IIT Kanpur, University of Waterloo, MIT, and also nanocomputing with Michigan State University. Dr. Tessmer is here, funding agencies, the collaborating institutes. Dr. Grover is unfortunately not here because of his health, but he's a great support with Michigan State University, Waterloo, IIT Kanpur, Delhi. And I'm grateful to Professor Premchand Satsangi Saab for introduction to this field. I'd like to end by a quote that, again by Niels Bohr. I can safely say that nobody understands quantum mechanics. This is just a brief introduction to quantum information systems and the various ideas that go into that. During the course of the school, you will get to hear several talks on more advanced topics. So this is that.